Hey everyone, and welcome. Today we're going to break down one of the most famous equations in all of science, F equals ma. And by the end of this, you'll see how this one simple formula basically runs the show on everything from pushing a shopping cart to the way the planets move. So, let's get into it. So let's start with a question you already know the answer to, just from, living life. Why is it so much harder to get a stalled car moving than it is to just pass a basketball? It seems completely obvious, right? One's heavy, one's light. But what's the physics behind that? Why does that even matter? Well, it all boils down to Newton's second law. At the very heart of this whole thing is this incredible relationship between force, mass, and a change in motion. And this isn't just some random idea. It's a fundamental law of how the universe works, and Newton just happened to capture it perfectly in one single powerful equation.
Okay, here's a really crucial point. Forces don't just cause motion, they cause a change in motion. And in the world of physics, any change in an object's velocity, and that could be speeding up, slowing down, or even just changing direction, we call that acceleration. So, get this in your head. A net force causes acceleration.
So what Newton figured out were two really simple, elegant relationships. First, the more force you apply, the more acceleration you get. Push twice as hard, you get twice the acceleration. Makes sense. But second, acceleration is inversely proportional to mass. This just means if you use the same amount of push, an object with double the mass will only get half the acceleration. And that, right there, that's our answer to the car and basketball question.
And here it is, the official definition, straight from our source text. It really is all about cause and effect, right? The cause is the net external force you apply, and the effect is the acceleration you get for an object with a certain mass. It's just so elegant, precise, and incredibly powerful when you think about it.
So when you put those two ideas together, you get this, probably the most famous equation in all of physics. Net force equals mass times acceleration. This is it. This little formula is basically the engine that drives all of classical mechanics. Every time you see something move, this equation is in the background, describing exactly what's going on.
Okay, so we've got the formula. But before we can actually use it, there's one skill that is absolutely critical. Seriously, it's the most important first step for solving pretty much any physics problem. And that's defining what we call the system. So what is a system? Well, it's actually super simple. It's just whatever object or group of objects we decide to focus on. Are we looking at the entire car or just one of the wheels? Are we analyzing the baseball or the baseball and the bat together? You basically just draw an imaginary circle around the thing you care about, and boom, that's your system.
Okay, so why do we even bother with this? Why does it matter? Because it lets us separate the forces that actually do something, the external ones, from the forces that don't. So let's say our system is a wagon with a kid in it. The push from a person outside the wagon, that's an external force, and it's going to make the whole thing accelerate. But what about the force of the child holding onto the sides of the wagon? Well, that's internal. It's not going to make the whole wagon start moving down the sidewalk, so we can just ignore it. And that right there is a huge deal. It lets us simplify things like crazy. All right, enough theory. Let's get our hands dirty and see how this thing actually works in the real world. It's time to put F equals ma to the test with a problem straight out of our source material.
So here's the scenario. We've got a lawnmower. Its mass is 24 kilograms. The net external force being applied to it, that's the push forward minus any friction pushing back, is 51 newtons. And the question is pretty straightforward. What's its acceleration?
Okay, step one. Let's grab our formula, F equals ma. But we're looking for acceleration, so we'll just rearrange it a little bit to A equals F over m. Step two, what's our system? Easy, it's the lawnmower. Now, step three, we just plug and chug. We substitute in the numbers we know. 51 newtons divided by 24 kilograms. And step four, we calculate the result, which gives us an acceleration of 2.1 meters per second squared. And there you have it. Simple as that.
Oh, and by the way, I've been saying newtons a lot. What even is a newton? Well, it's the official unit of force. And here's the cool part. Its definition comes directly from the F equals ma equation. See? 1 newton is just the perfect amount of force you need to take a 1 kilogram mass and accelerate it at 1 meter per second squared. The units are literally built to work together perfectly.
All right, let's tackle something that trips up so many students in physics. We've got to clear this up right now. Mass and weight are absolutely, positively not the same thing. Here's the bottom line. Mass is how much stuff, how much matter is inside an object. We measure it in kilograms, and it never, ever changes no matter where you go in the entire universe. Weight, though,
That's a totally different beast. It's a force. Specifically, it's the force of gravity pulling on your mass. We measure it in newtons, and it definitely changes depending on where you are.
And you can actually see this perfectly in the formula for weight itself. W equals m times g. Does that look familiar? It should. It's literally the same structure as F equals ma, because it is F equals ma. Weight is the force, mass is still mass, and g is just the special name we give to the acceleration caused by gravity. And this example just makes it crystal clear. Imagine a 75-kilogram astronaut. Her mass, the amount of stuff she's made of, is 75 kilograms on Earth, and it's still 75 kilograms on the Moon. That doesn't change. But on Earth, gravity's pull is a hefty 735 newtons. On the Moon, where gravity is way weaker, that same 75 kilograms has a weight of only 125 newtons. See? Same mass, totally different weight.
Okay, pop quiz time. Let's see if this is sinking in. Think about your bathroom scale. When you step on it, what's it really measuring? Your mass, the constant stuff you're made of, or your weight, the force pulling you down?
And the answer is, it's measuring your weight. A scale is basically a spring that gets compressed by the force of gravity pulling you down. But since most of us don't care about our weight in newtons, the scale does a quick little calculation for us. It takes your weight, divides by Earth's gravity, and then shows you the result as your mass. It's actually a pretty clever little trick, right?
Phew, okay, that was a lot. So let's wrap this up and boil it all down to the key things you absolutely need to take away from this. Think of it as the big 4 takeaways. 1. Forces don't just cause motion, they cause acceleration, a change in motion. 2. That whole relationship is all wrapped up in that beautiful little formula F equals ma. 3, and this is a big one, always define your system first. It makes life so much easier. And 4, mass and weight are not the same thing. Mass is your stuff, weight is gravity's pull on your stuff. If you've got those 4 ideas down, you're in great shape.
So I'll leave you with one last thing to chew on. We just used F equals ma to understand a simple lawnmower, but the pull of gravity is also a force, and a giant planet is also a mass. So how could this same simple rule be the key to unlocking something as gigantic and majestic as a planet orbiting a star? It's something to think about.